All right, so we're going to look at some problems from organic chemistry subject test. This is in preparation for the DAT. So if we look at question 6, we have a molecule of sulfonyllic acid, and of course its structure is given in the problem. It can be recrystallized from hot water and has an extremely high melting point relative to its molecular weight. So we want the best explanation for its physical properties. So let's look at these one at a time. A states the amino group of sulfonyllic acid acts as a Lewis acid. The fact that it can act as a Lewis acid isn't going to strengthen its physical properties in terms of its high melting point, because this can be protonated at certain pHs. This can certainly be deprotonated at certain pHs, much like an amino acid can be. So if it lost its proton, it's losing its positive charge. That would decrease the melting point. So I think we can eliminate A effectively from this question. B, the sulfonyllic acid exists as a pair of enantiomers. You really aren't going to do that on DAT because then you're looking at chiral planes. I would skip quickly past B. I would skip quickly past C. It exists as a pair of diastereomers. All of your carbons are sp2 hybridized. The sulfur atom of sulfonyllic acid has an unusually low oxidation number, actually has an unusually high oxidation number. That's absolute falsehood. So we're left with D. Sulfonyllic acid exists as a Z-ion. This can be deprotonated, this can be protonated. It's a dipolar ion, has a very high dipole moment. The high dipole moments resulting from the IMFs are going to result in very high melting points, very high boiling points, etc. So the best answer indeed is D. So whenever you're looking at unusually high melting points, you need to think in terms of, I have a significantly important intermolecular force, or IMF. Which answer choice accounts for that? And in this case, it is D. So moving along to the next question. Which of the following is the most stable carbocation? So let's actually go to the easel and review a bit about carbocations. There are two stabilizing forces in carbocations. One of these stabilizing forces is going to be the inductive effect. And the other stabilizing force is going to be the resonance effect. So let's first talk about inductive effect. I can have a carbocation that can be classified as methyl, as primary, as secondary, or as tertiary. If we take a closer look at the tertiary carbocation versus the secondary carbocation versus the primary carbocation versus the methyl carbocation, we're going to find a key difference in an orbital interaction that is designed to stabilize the empty p orbital in all four of these structures. If I put all of the other carbons in the same plane, I have a p orbital lobe that comes out of the plane of the screen towards the viewer. I have a p orbital lobe that goes into the plane of the screen away from the viewer. In a carbocation, this p orbital lobe is absolutely devoid of any electron density. So what is relevant is that the carbons that are attached to the carbon with the carbocation are bonded to hydrogen atoms. So remember, with tetrahedral geometry, you have two of the four bonds are in the same plane. The third bond must come out of the plane, and the fourth bond must go into the plane. What this means is that the carbon-hydrogen bond, which is very slightly polarized, has an electron pair that can weakly overlap with the p orbital lobe that's coming out of the plane of the screen, while the carbon-hydrogen bond that's going into the plane of the screen, due to the fact it is weakly polarized, can overlap its electrons with the p orbital lobe going into the plane of the screen. This helps to stabilize that empty orbital. I can do this 1, 2, 3 times for the front orbital, or the orbital that's coming out of the plane of the screen. I can do this 3 times to the back orbital, the orbital that's going into the plane of the screen. So a tertiary carbocation has 6 favorable orbital interactions. To be even more specific, these are sigma pi orbital interactions. The tendency of polarized sigma electrons to weakly overlap with empty p orbitals in order to stabilize those orbitals is known as hyperconjugation. Hyperconjugation is the scientific explanation for why a tertiary carbocation is more stable than a secondary carbocation, which is significantly more stable than a primary carbocation or a methyl carbocation. In fact, tertiaries and secondaries have been isolated in nature. Primaries and methyls have not. That's the inductive effect. There is also a resonance effect. Resonance effect is going to take place in a molecule in which a resonance structure can help to stabilize the positive charge by delocalizing it. So I delocalize the charge. In this particular resonance structure, I can push my pi electrons from C1 and C2 to C2 and C3 because C3 is sp2 hybridized, just as C1 and C2 are sp2 hybridized. And now the positive charge is on a primary carbon, but more importantly, it's allylic. So allylic carbocations are resonance stabilized. More importantly, benzylic carbocations are resonance stabilized. In fact, they're stabilized to a larger extent. I can push pi electrons, and in fact there are certainly more than 2 possible resonance structures that will stabilize the benzylic carbocation as I have drawn it. There's one such resonance structure. would be a second. And I'll stop here because simply all I'm proving at this point is that I have more resonance stabilization for the carbocation when I have a benzylic functionality, that's a carbocation, versus when I have an allylic functionality. So this is benzylic. The resonance effect explains why benzylic carbocations are more stable than allylic carbocations. Now here's the rub. There is a competition between the resonance effect and the inductive effect. And the daddy is the resonance effect. The resonance effect trumps the inductive effect in organic chemistry in nearly every circumstance, and I'll go ahead and give you the exception right now, unless I have a halide. A halide has a greater inductive effect than it does resonance effect. In fact, this is why chlorine, fluorine, bromine, and iodine are orthoparadirectors, but they're deactivators, because the resonance effect with a halide is not as significant as the inductive effect. Halides are not very adept at making two bonds. They much prefer to make a single bond. They're essentially monovalent atoms. There, of course, are exceptions to that when they're bonded to one or more oxygens. But in the organic world, we rarely see a halide that's making more than one bond. And when we do, it's a short-lived intermediate, like a bromonium ion intermediate from electrophilic addition. So benzylic, putting all this together, for carbocations, benzylic is the most stable. Then allylic. Then tertiary. Then secondary. Then primary. And really in a list, we have methyl, we have phenylic, we have vinylic. These are all very unstable carbocations. So phenylic means that we would have a positive charge on one of the benzene carbons. There's no resonance stabilization for this. By the way, this is the classic M to Z base peak of 77 that's observed in aromatic compounds, while the benzylic position, being much more stable in terms of resonance, is the mass to charge of 91. So if I have a benzylic bromide, the base peak that dominates the mass spec is 91, not 77. But if I have bromobenzene, it's 77 that dominates and not 91. In the mass spec, this actually rearranges to give an aromatic ion called a tryptolium ion, which is an aromatic 7-membered ring. And this is where we get the mass to charge of 91. So let's go back to the question now and put all of this together. Which of the following is the most stable carbocation? And what I'm going to do is I'm simply going to put a descriptor to the left for each answer choice. A is a classic vinylic. Some of you guys probably aren't old enough to remember, but there was a very, very famous song in the early 90s about Vanillic Ice Ice Baby. I don't know if you remember that or not. But if you want to stop, collaborate, and listen, Doc Oz got a whole new invention. B is allylic. That's going to be our best answer choice unless I have a benzylic. Notice I do not. C is primary. D is primary. E is homobenzylic. In organic and in biochem, we use the prefix homo to mean one more carbon than normal. If the positive charge was on the CH2 bonded to the aromatic ring, E would be the best answer. But as it is, B is the best answer because it's the only one capable of resonance stabilization. All right, so moving to a new question. We have a compound that's separated from an ether mixture by extraction with cold aqueous sodium bicarbonate. Okay, stop right there. This sodium bicarb is an exceptionally weak base. It will only deprotonate the most reactive of organic acids. We now know we have a carboxylic acid. So we don't have one for A, that's an alcohol. B is an aldehyde. C is an amine. D is a carboxylic acid. E is a carboxylate. We're going to use this to extract D from the mixture. It deprotonates it. So this would already be deprotonated in the mixture, so sodium bicarb would have no effect. We deprotonate it, which makes it more soluble in water. Then we'll reacidify it, which is what we do when we add HCl to the extract, and to obtain a crystalline form of this acid. So we have a C9 acid, so nonanoic acid. And that's really the only identity of the compound that's possible given these conditions. Remember, we extract acids with bases. Now, it's true that many different functional groups can act as acids, but let's just look at this for a moment. There's no real ionizable proton that's available to be deprotonated in E, nor is there in B. This proton has a pKa of 38. This proton has a pKa of 16. This one has a pKa of 17. This one has a pKa of 50 to 60. This one has a pKa of 4 to 5. This is definitely the most reactive acid I have. This is the answer I want. So again, to recap, we will deprotonate with a base to make it more soluble in water. We'll extract it from the ether so that we have only the aqueous solution. Then we'll reprotonate with a protic acid like HCl. It will become less soluble, and then we separate the solid from the water mixture with a simple filtration step. So the best answer for number 8 is D. Moving on to number 4. Cyclopentadiene reacts with sodium metal at low temperatures according to the following reaction. Why does this reaction proceed? You have a non-aromatic compound that becomes aromatic. So aromaticity, bam, E. Enough said. Let's talk for a minute about how we can determine that this molecule becomes aromatic. So let's talk for a moment about the chemistry of Frost circles. A lot of courses will really skimp on aromaticity, and I think that's really unfortunate because it's some pretty important chemistry, and it's all about the aromaticity of this molecule right here. Cyclopentadienyl carbanion. I have 6 pi equivalents, and this is a legitimate pi equivalent because of resonance. I'm only going to show one of these resonance structures. Let's be progressive and use pink today. What do you say? So this is how a Frost circle works. We are going to inscribe this 5-membered ring into a circle with one of the apexes of the polygon at the bottom of the circle. Now I'm not going to actually draw the circle because I don't need to answer this question. Everywhere where the circle will intersect the polygon becomes a molecular orbital. So we have one right here, one right here, one right here, one right here, and one right here. 6 pi electrons. Here's 1, here's 2, here's 3. Now remember, these are degenerate in energy. I have to put 1 in each one to satisfy Hund's rule. Here's 5, and here's 6. This is the highest occupied molecular orbital. Yet another use for the term HOMO. Highest occupied molecular orbital, lowest unoccupied molecular orbital. A molecule is aromatic if it is 1, cyclic, 2, there is an uninterrupted, notice how I interrupted the word interrupted, array of p orbitals. And 3, I have a completely filled highest occupied molecular orbital. This is a classic aromatic compound. 5-membered ring with 6 pi equivalents is aromatic. So if we go back to our question, this is non-aromatic because it does not contain an uninterrupted array of p orbitals. I have one on this carbon, one on this carbon, one on this carbon, one on this carbon, but this is sp3. It is interrupted. However, when I remove one of the hydrogens and leave behind a lone pair, this is now sp2 hybridized because of resonance. It's an aromatic compound. So I think we're on number 5 now. A mixture of alkyl halides is subjected to elimination with 1 mole of aqueous acid and alcohol. If the reactant mixture initially contains 1 mole of each of N-propyl chloride and isopropyl chloride, what can be predicted about the product mixture? So let's put this on our canvas. I have N-propyl chloride and I have isopropyl chloride. Now, it tells us in the problem that these are going to be subjected to an E1 elimination, which means I will have, and this is the real issue in this question, it's one of carbocation stability. So the E1 mechanism dictates that we have a carbocation intermediate. So we will preferentially form the secondary carbocation over the primary carbocation because of hyperconjugation. This means the elimination product that I form should be formed preferentially from the isopropyl chloride and little to none of the primary alkyl halide should react, because the activation energy barrier for making a primary carbocation is really, really high. And just to give you a little visualization there, let's do this little magic. They would form the same product, but the difference is here's our activation of energy barrier for the isopropyl chloride as opposed to our activation of energy barrier for the N-propyl chloride. And so the molecule that reacts is going to be the molecule rendered in orange and not in red. So at the end of this reaction, this should be unreacted starting material that still remains in the system. A single alkene product is formed and N-propyl chloride is present in excess. You cannot form via the E1 mechanism two different products with this reaction, because when this eliminates, you get the same product as when this guy eliminates. There's only one product. That leaves one, actually that is the end of all of these problems. So I'm going to end this particular OzCast for now, and we'll pick up with some others.